Hi, all my YouTube viewers. It's Crystal here. I just want to give you another code review, and this code review is LSTM better than RNN in predicting on the prices of Bitcoin. And in this particular piece of code, which is written in Python using Google Colab, what I have done is I've used an LSTM in place of an RNN, which I have previously used. So what I've done is I did a little bit of research, and the LSTM that's a long short-term memory, is an improved version of the recurrent neural network, that's RNN, designed by Hochreiter and Schmidheuter. LSTM is well suited for sequence prediction tasks and excels in capturing long-term dependencies. Its applications extend to tasks involving time series and sequences. LSTM's strength lies in its ability to grasp the order dependence crucial for solving intricate problems such as machine translation and speech recognition. So that's just a little bit of information that I've got whilst researching LSTM. And so now what we'll do is we'll do the code review. So the first thing we want to do is we want to import the libraries after we have created our Jupyter notebook. So we're going to import pandas as PD to create the data frame and process the data. We want to import NumPy as MP to create NumPy arrays and perform numerical computations. We want to import datetime to timestamp the dates. We want to import math to carry out mathematical computations. We're going to import sklearn to provide machine learning functionality. We're also going to import TensorFlow to define the neural network. We're going to import matplotlib.pyplot as PLT to visualize the data, and then we're going to import matplotlib.dates to visualize the data in date format. And we're also going to import Seaborn as SNS to statistically visualize the data. And so after we have imported all of our libraries, we're going to use pandas to read the file. I got the file off of Bitcoin. Unfortunately, I can't show that to you because I'm using a free screen recorder, which will only let me record one tab at a time. But I downloaded the Bitcoins, and then I saved it onto my Google Drive. And then I created a data frame from it. And so with the data frame, you had the start, end, open, high, low, close, volume, and market capitalization. We checked info, and you can see that the first two columns of data are objects, and the remaining columns of data are numeric. We're going to check for null values, and there's no null values, so we don't have anything to impute. If you were going to impute anything, I think that you would have to use pandas, and then you would have to impute it for time series. Now we're going to use date time to timestamp the date. So now you can see that the date has been timestamped. We're going to extract our features, end and close, and these features are going to form our data set, closing data frame, closing BTC. Now what we're going to do is we're going to use Matplotlib to graph the end figures against the date. So you can see that this is what the prices looked in each date from 2001 to 2004. We use Seaborn to create a histogram so you can see the distribution that it makes. And now what we're going to do is we're going to we're going to look at the year 2023. These are the prices of the year 2023. We're going to look at the October to December trend in 2023. And so you can see that the prices are gradually increasing. And now what we're going to do is we're going to use stats models, and we're going to form a seasonal decompose of the time series. So the first thing that we will do is we will do a multiplicative decompose. So here is your multiplicative decompose, and then so if you're really into statistics and you really want to study it, then that will give you a lot of information. And so with the multiplicative decompose, you get the trend, the seasonal, and the residual. And then after the multiplicative decompose, then we're going to do the additive decompose. And again, that gives you the trend, the seasonal, and the residual. So if you really like statistics and you really want to study the time series, Stats Models is a good library to use. So now what we're going to do is we're going to, from the date, we're going to extract the features from the date. So you're going to get year, month, day, day of week, week, day, name. And then we're going to have the features, and we're going to create a new data frame from that, calling it closing BTC dates. So here is the data frame that it makes. So you see that you've got your end is your index, and then you've got your close, year, month, day, day of week, and weekday name. So we've got a box plot of the months, so you can see the traffic for each month of the year. Got a box plot for the year, so you can see the traffic for each year. And so 2024 had the most traffic. Got a box plot for the day of the week, and so you can see that each day of the week was similar. And now what we're going to do is we're going to timestamp. We're going to time resample. So the first thing we're going to do is the end of the year. So this is the bar plot for the end of the year, and you can see that 2024 had the most traffic. Do a bar plot for the beginning of the year, and again you can see 2024 again had the most traffic. Now we're going to do a bar plot for the months, and so it gives you the traffic for each month, which is good. And then now what we're going to do is we're going to do something called rolling windows. So the first one, we're going to roll at 1 point, which it would not allow me to roll at 0 points. So I had to roll at 1 point. And then the next one is we're going to roll at 30 points or 30 days. And so you can see that the time series is much smoother when you roll it. So now what we're going to do is we're going to go into the deep learning portion of the program, and we're going to create a new new data frame called an MLBTC. And so that you're going to have your end is your index, and then your close is your column. And then what we're going to do is we're going to reverse it, because you want the first day, the earliest date to be at the top of the data frame, and then the last date to be at the bottom of the data frame. So now what we're going to do is we're going to set our training and validation sets, and your train length is going to be 80% of the length of the data frame. And so your training data is 80% and your validation data is 20%. So we've just checked the validation data so you can make sure that the validation data is correct. And now what we're going to do is we're going to scale the the train data and the validation data using sklearn's min-max scalar to make sure that that the predictions are between 0 and 1. So you can see that. And then after we've done that, what we're going to do is we're going to create our X train and our Y train. And the reason why is because you have to convert this to a supervised learning set in order to get it to work. So we've converted it to X train and Y train using a range of 50. So and then we're going to convert the validation set to xval and yval using a range of 50. So now what we're going to do is we're going to convert the training sets and the validation sets to NumPy arrays, and then we're going to reshape them to get them to work with the LSTM. And now what we're going to do is we're going to import all the TensorFlow and Keras libraries, and that's what's going to create our deep learning model, which in this case is going to be an LSTM. And then so I set the seed at 42 just to try to make sure that all the predictions are within the same range every time you run them. So we're going to initialize the LSTM. We're going to have a sequence length of 50. The regressor is going to be sequential. So the first row is going to be an LSTM row. And then the second layer is going to be a dropout of 0.2. Then we're going to have another LSTM layer, and then we're going to have an output layer, which is going to have an activation of sigmoid. Then we're going to compile the LSTM. We're going to use the optimizer of SGD with a learning rate of 0.01, momentum of 0.9, Nesterov equals true, and loss equals mean squared error. And then what we're going to do is we're going to train the data, and then for 30 epochs. And then when we train the data for 30 epochs, this is the output that we get. And it looks like it may have improved if I trained it for 40 epochs, because it still looks like it was going down. So you never know. So now we make predictions on our validation set, and we scale it. We reverse scale the validation set, and then we reverse scale the predictions. And when we do that, we have an RMSC of 2652. And I would like to say that that is still higher than the RMSC for the RNN. So in this particular case, the LSTM did not perform as well as the RNN, and I only trained the RNN for 20 epochs, and I trained the LSTM for 30 epochs. So it had more training time, but still the error was still higher. Created a data frame so you can compare the actual values against the predicted values. We take the actual values and we superimpose them over the predicted values, and you can see that. And this is what a diagram of the time series looks like. So you can see that it's okay, but it's not as good as the RNN that I had done in a previous video. And so the answer to the question is, in this particular situation, an LSTM did not outperform an RNN. The RNN performed better, and that's the answer. So in this particular situation, I would use the RNN and not the LSTM, but it's also everybody's personal choice, because you could tweak it. You could use a different optimizer. You could use a different training time. You could train it for more, because there's a possibility that if I trained it for 40 epochs instead of 30 epochs, that I may have improved error rate. So there are still things that you can do to try to improve the error of the model. But I'm going to go ahead and close this video because I've covered everything that I want to cover. So thank you for watching my video. If you like my video, please like and subscribe. And I look forward to communicating with you in the next video.